And up next, we have Markus Kindler from Form Factor. It's a recording, folks. So just to let you know up front, this is a recording. He was not able to be with us live, but one of his colleagues, um, Fernand Wimmer, will answer questions after the video. So Markus is with Form Factor, ATT. Markus is serving as the ATT Systems Manager Director since 2008. In this role, Markus is the head of sales and marketing, as well as ATT's service support group. And moreover, he is the technical link between the end user and AT&T R&D's department, ensuring that ATT's product development addresses future concerns or actual problems. Prior to joining ATT, Markus served at Form Factor as general manager for the Qimonda constellation. So I believe we can go and start this video.
Hello everyone, and a very warm welcome to the third session of today's workshop. My name is Markus Kindler, and I'm one of two managing directors at ATT Systems. It is my honor and great pleasure presenting at the MEPTEC Too Hot to Test conference today. At ATT, we are focusing on advanced thermal systems for the electrical wafer test. Our systems and solutions are applied on fully automated volume production probers, as well as on semi-automated and manual probers for engineering or device characterization. We are in the market for 20 years now, supporting an installed base of over 6,500 systems, utilized for a wide range of applications at a large customer base. Just one remark before we start the discussion. This presentation has been pre-recorded for time zone reasons. There will be a Q&A session at the end, and I would like to ask you to note or remember your questions or comments and address it at the end of the presentation. Okay, in the next 25 or 30 minutes, we will discuss challenging high power applications from a thermal chuck point of view. I believe that I'm not telling a secret by saying that the electrical test conditions are getting extremer. For example, full wafer DRAM testing is generating 2000 watts and more. Is it possible to dissipate this high amount of energy at low temperatures and at high temperatures with a single test cell setup? AI devices are facing high power densities due to the small die size. This results in high junction temperatures, causing burned probes and inaccurate test results. How can we control the chuck and device temperature at low and high temperatures? Is it too hot to test? For sure, it's getting more challenging to control the chuck and the device temperatures. Therefore, advanced thermal systems need to have low thermal resistance, active temperature control with a smart arrangement of control sensors, and high cooling capacity through liquid-cooled chillers. In other words, active temperature control is crucial, and the thermal system is an integral part of the test cell. The good news is that some solutions already exist. However, there are also some challenges that remain at the same time. Let's briefly recap. What is a thermal chuck system? The thermal chuck system consists of the thermal chuck, the temperature controller, and maybe a cooling booster for controlled ambient up to plus 200 degrees applications without a chiller. For cold probing, there are two options: air-cooled chillers and liquid-cooled chillers. Both methodologies offering different chiller configurations for different temperature ranges, maybe minus 40 degrees C or minus 60 degrees C. Ideally, the chuck and the controller can be used for both methodologies, air-cooled and liquid-cooled, for highest operational flexibility. The next slide shows high-level requirements that we are seeing today when a customer contacts us. Common requirements are power dissipation ranging from 300 watts up to 2000 watts, and this is the topic that we are discussing today. High voltage up to 12 kilovolt and high current up to 300 amp. Electrical leakage and noise of less than 100 femtoamp at 10 volt and less than 10 nanoamps at 3 kV. Of course, temperature control performance like accuracy, stability, and uniformity. Mechanical requirements like planarity of 10 micron and high rigidity up to 500 kilogram force. And typically, it's not a single requirement, but a multi-dimensional requirement. For example, high power dissipation means high power dissipation at the wide temperature range and at uniformity. So this means that we need to transfer a high amount of energy while maintaining a very good temperature uniformity across the wafer. For this workshop, we prepared 3 examples for different high power applications, covering pretty much what most of our customers are requesting today. The first example is full wafer contact. This is mainly for DRAM, flash, and high bandwidth memory testing. The applied power per die and the power density are relatively low, but the parallelism is high with over 2000 dies per touchdown. This can add up to around 2000 watts that needs to be dissipated to control the temperature. Testing temperature range is -40 degrees C up to 125 degrees C. The second example that we are covering is a microcontroller for the automotive industry. The contact area is around 10,000 square millimeters. The applied power per die is medium to high. The power density is higher compared to the first example due to the smaller contact area. The required heat dissipation is up to 1000 watts. Finally, we will cover small or single devices like graphics processing units or 5G devices. The contact area is very small, the parallelism is low, but the power density is quite high with up to 125 watts per square centimeter. The applied power depends on the product and can be up to 500 watts at this point of time. The temperature range is the same as for the first 2 examples. Basically, heat or power dissipation means to transfer a thermal load away from the substrate, the wafer, or the device under testing. If the thermal load is larger than the heat dissipation capabilities of the thermal system, the chuck temperature will start to increase and cannot be controlled anymore. The rule of thumb is that the cooling capacity of the thermal system must be larger than the thermal load. As we learned earlier, there are 2 different cooling methodologies, air-cooled and liquid-cooled. Some customers are asking us why we use liquid-cooled systems for high-power applications. The simple answer is because liquid-cooled systems have a significantly higher cooling capacity compared to air-cooled systems. So let's check why this is the case. So, where's the thermal load coming from? In idle mode or standby mode, we have a thermal load through convection. Let's assume that the chuck temperature is at -40 degrees C. The thermal load through convection depends on the temperature difference. In our case, the delta T is 65 Kelvin, assuming that the ambient temperature is at +25 degrees C. Then the heat transfer coefficient and the surface area. So this gives us a thermal load through convection of around 130 watts. Additionally, there are another 50 watts from the stage. This gives us a total thermal load of around 180 watt at -40 degrees in standby mode. So this means that we need to dissipate around 180 watt just to keep the chuck temperature at -40 degrees C. No testing, no needle contact, just to keep the temperature stable at -40 degrees C. So we have around 180 watt in idle or standby mode. But the systems are not used to operate in idle or standby mode. So let's have a closer look at the thermal load during testing. This example is based on DRAM testing, and honestly it's not the latest technology. But the purpose today is to give you an understanding of the range and the magnitude. During testing, we see energy or heat from the probe card and from the device itself. The energy from the probe card depends on the beam count, probe card size, probe card technology, and other factors. The energy from the device depends on the testing power. In our example, we assume a testing power of 600 milliwatt per die. Looking at the 1024 DUT example, we need to dissipate around 550 watts from the probe card and around 614 watt coming from the device. So the total thermal load during testing can be easily around 1100 watt, on latest technologies even over 2 kilowatt. The total thermal load is a function of the thermal load in idle mode and the thermal load during testing. And at minus 40 degrees chuck temperature, it can range from 230 watt up to 2.2 or 2.3 kilowatt. So now we understand how much energy we need to dissipate during the electrical wafer test. To choose the right cooling methodology, we need to understand the cooling capacity of air and liquid-cooled systems. Our calculations are based on the assumptions that the efficiency factor of the heat exchanger is 1, meaning that we have a 100% efficiency. The heat exchanger is built into the chuck. So let's start with the air-cooled system at the chuck temperature of minus 40 degrees C. The cooling power is a function of the specific heat capacity, the thermal mass, and the delta T. The delta T is the temperature difference between the coolant inflow temperature and the coolant outflow temperature. The thermal mass is a function of the airflow. In our case, it's 320 liters per minute, and the density of air. The coolant inflow temperature has been set to minus 80 degrees C and the coolant outflow temperature to minus 40 degrees C. Actually, it cannot be higher because if the coolant outflow temperature would be higher than minus 40 degrees, then the chuck temperature would start to drift. So now if you put our values into the equation, then we can calculate a maximum power of around 275 watt at minus 40 degrees chuck temperature. Now we also need to remember the thermal load in standby or idle of 180 watt. So this 180 watt need to be subtracted from the 275 watts. So this means that we have only around 100 watt left to dissipate energy coming from the wafer test. So how does this compare with a liquid-cooled system? The heat dissipation process is basically the same, but if we look at the properties of the thermal fluid, then we can realize that the density is much higher compared to air. And higher densities basically mean that we can transfer larger amounts of energy. And this is the main reason why liquid-cooled systems have a significantly higher cooling capacity or cooling power compared to air-cooled systems. So again, the heat dissipation process is the same. Due to the high density of the thermal fluid, we can set the coolant inflow temperature to minus 50 degrees C, and the coolant outflow temperature is again minus 40 degrees C, and it cannot be higher. And this gives us a delta T of 10 Kelvin. So let's quickly do the calculation here. With the given density and the coolant flow rate of 10 liters per minute, we can calculate the thermal mass with 18,000 grams. And this is more than 40 times higher compared to the air-cooled system. The specific heat is similar. The delta T is 10 Kelvin, and therefore the calculated maximum power is over 3,000 watt, which is an order of magnitude higher compared to the air-cooled system. Another positive aspect of the liquid-cooled system is that due to the higher cooling capacity or cooling power, the delta T between the chuck temperature and the coolant inflow temperature is only 10 Kelvin compared to 40 Kelvin on an air-cooled system. Lower delta T's greatly help to get better temperature uniformities. Okay, let's summarize. Liquid-cooled systems provide significantly larger cooling capacity. The temperature difference between chuck and coolant is notably lower, which means better temperature uniformities. And these are the reasons why we choose liquid-cooled systems for high power applications. Now we understand that we need to use liquid-cooled systems. But what is multisense and why do we need it? The simple answer is because you only can control what you can detect. But let's have a closer look. Let's come back to our three examples. Example 1, full wafer contact testing. Most thermal systems have one control sensor, which is at the center of the chuck. And this is enough for this kind of application because the energy or power is distributed uniformly across the chuck. But what about smaller contact areas? If the touchdown is in the center, then there's no problem to detect the temperature change. But the system is more or less blind if the touchdown is outside of the center. So this means what we basically need is we need an Argus or all-seeing kind of system with multiple sensors across the chuck. And for smaller devices, even more sensors. And this is what we call multisense. Each individual sensor can be the control sensor, depending on the detected temperature change. The number of sensors inside the chuck is limited due to the complexity of the chuck. Number of add-on sensors is scalable. We are doing tests right now with up to 25 sensors, but I can't share more at this point of time due to the early stage of this project. All data that I will show on the following slides have been gathered utilizing our LTR chuck system with 9 temperature sensors and with liquid cooled chillers. So this slide shows the test setup for the full wafer contactor tests. We use the sealed test box, our 300mm LTR chuck with 9 sensors, our L80J liquid cooled chiller, and a multi-range power plate with up to 2000 watt, which was put on top of the chuck system to simulate the full wafer contact touchdown. The first graph shows the test results at plus 25 degrees C. The red line here is the chuck set temperature, and the green line reflects the actual chuck temperature. What you can see is when we turn on the 2000 watt here, then the temperature will increase by around 1 degree C. And then the system is able to fully dissipate the 2000 watt and to control the temperature exactly at the set point. So this means that we are able to dissipate 2000 watt at 25 degrees C and to control the temperature within 1 Kelvin. The next slide shows the results at minus 40 degrees C. And here again, the red line is the chuck set temperature, and the green line is the actual chuck temperature. When we turn on the 2000 watt, the temperature will increase, in this case by around 2 degrees C, and then the system is able to fully dissipate the 2000 watt and to control the temperature at the set point. So also at minus 40 degrees C, we are able to dissipate 2000 watt and to control the temperature within 2 Kelvin. And then the last test for the full wafer contactor at plus 125 degrees C, and exactly the same picture. In this case, the temperature increases to 126.7 degrees C when applying the 2000 watt, and then the system can fully dissipate the energy and can control the chuck temperature very close to the set value. So the second example is a 100 by 100 millimeter contact area. We used again our sealed test box, our 300 millimeter LTR chuck with 9 sensors, but we used a smaller chiller, actually with less cooling power, and we used a smaller power plate to reflect the smaller contact area. We used a different chiller because this customer already had an installed base of L60J chillers, and they wanted to see if they can upgrade their existing installed base with the LTR and multisense functionality. The first graph shows the test results at 0 degrees C. Top position with an applied power of 400 watt. This area here is the standby period. So this means the period before we turn on the power, and you can see that all the sensors are very close around the set temperature of 0 degrees C. Then here we turn on the power, 400 watt, and we can see a temperature increase of around 1.6 degrees C. RTD7 detects the temperature increase and became the control sensor. And then the system is able to fully dissipate the energy and to stabilize the temperature very close around the set value of 0 degrees C. The other temperature sensors can be ignored because they have no impact on the contact area. This graph shows the results at the center position. So after applying the power, the temperature increased to around 2 degrees C, and then the system fully dissipates the energy and can control the temperature very stable around the set value. Same picture at the tube position. In this case, RTD3 became the control sensor, and the maximum temperature was measured with 1.4 degrees C before the system fully dissipates the energy and controls the temperature very stable around the set temperature of 0 degrees C. Then we changed the jug temperature to plus 105 degrees C and basically repeated the test. Top position with 400 watt. Again, RTD7 became the control sensor. The maximum temperature reached 105.8 degrees C after applying the power. Then the system dissipated the entire energy and was able to control the temperature very stable around the set temperature of 105 degrees C. At the center position, exactly the same behavior. Maximum temperature was measured at 105.9 degrees C. The energy was fully dissipated, and then the temperature was very stable around the set value. The last test has been done at the tube position, and here exactly the same picture. RTD3 became the control sensor. The maximum temperature was around 106 degrees C, full heat dissipation, and then very stable temperature control around the set temperature. Okay, the last example is for our small devices, 23 by 23 millimeter contact area. We use the same test setup as before, the sealed test box, LTR jug, 9 temperature sensors, L6J chiller. Of course, we used a different heater plate to reflect the smaller contact size. This heater was able to provide a maximum power of 200 watt, and actually this was the most powerful one that we could get during that time. This customer asked us to test two different conditions, 0 degrees C with 100 watt and plus 105 degrees C with 160 watt. The test time was 4 minutes at 0 degrees C and 15 seconds at plus 105 degrees C. The goal was to control the temperature increase within 3 degrees C. Okay, the first test was done at 0 degrees C at the top position with an applied power of 100 watt. RTD7 detected the temperature increase, and the maximum measured temperature was around 1.4 degrees C, and then the system was able to fully dissipate the energy and to control the temperature within plus minus 2 degrees C. At the tube position, exactly the same picture. RTD3 became the control sensor. The maximum temperature was 2.3 degrees C, and the system was able to fully dissipate the energy and to control the temperature within the plus minus 3 degrees range, which was specified. Then we changed the temperature to plus 105 degrees C and tested the system capability with an applied power of 160 watt. First test was done at the top position. The test time was 15 seconds, and RTD7 became the control sensor, and the system was able to keep the temperature below the specified 108 degrees C. The second test has been done at the tube position. RTD3 became the control sensor. The maximum temperature was 107.8 degrees C and also within the specified limit of 108 degrees. Let's summarize. High power dissipation requires liquid-cooled systems due to the high cooling capacity and better uniformities. We are able to dissipate 2000 watts for full wafer contactor applications like DRAM, flash or HBM testing. This solution is currently on the way to volume production. 100 by 100 millimeter contact areas, we have good results up to 400 watt, and first installations for volume production are happening right now. Higher cooling capacity is basically possible with more powerful chillers. Small contact areas, we demonstrated the ability to dissipate 160 watts with our L60 chillers. This solution has been adopted in production for 5G devices already. Higher cooling capacities are also possible with more powerful chillers. The next step is to evaluate a new chuck type with more temperature sensors like 21 or 25, and I think we should have the first results within Q2 this year. A few words regarding the thermal fluid. At this point of time, we can cover a temperature range from -40 degrees C up to +125 degrees C with a single fluid. A wider temperature range requires a thermal fluid with a higher boiling point and lower viscosity at low temperature. Existing fluids offer either a high boiling point or low viscosity at low temperature. So this means that we need to develop new thermal fluids to cover a wider temperature range. Or alternatively, we need to dedicate the test cells for certain temperature ranges. For example, one test cell could be used for a temperature from -60 degrees up to ambient, and another test cell could be used from ambient temperatures up to, let's say, +175 degrees C. So this basically concludes my presentation. Thank you very much for your attention. I think we should have a couple of minutes left for a Q&A session. Thank you very much.
Bernard, we have some questions. On slide 16,
sure.
on slide 16, I don't know if you have the slides yourself, but the time duration.
The test time at slide 16 was 11 minutes. That was a 2 kilowatt test, yeah. That means the power plate was running for 11 minutes.
Okay. And it says, why is one RTD sensing much higher than the other RTDs?
Is it referred to a special page? No, it's not. If we do the temperature monitoring and the temperature regulation on one RTD, the others are not important because we're just controlling this one RTD at this point, and the other sensors can be lower, and that's not important for the final test because only current RTD which is in contact with the testing device is responsible and important for the full test.
Yep, yeah, that's exactly right. So just to kind of add to your comments, so that was talking about centralized, so small, only a small section was being tested. The other areas, there's no test going on, so that's why they're low.
Yes,
so,
right. Yeah,
okay.
and we are switching always to the right sensor where the contact area is, and then we can react and control this area.
Ferdinand, a question just for clarification. The time scales shown are in minutes or seconds on the
These
slide?
are in minutes.
Right.
Time scale
So,
are in minutes, yeah.
Have you guys characterized how long it takes for, let's say, the die, the load, how long it takes for the load, what's the thermal delay from when the load hits the temperature to when the sensor reads that temperature? What's sort of the lag?
The lag, it's around seconds actually, because the thermal load what we are using have a very high thermal mass compared to the wafer, because it's a regular heater device, and then the thermal mass has a big influence on this test. But the reaction on the chuck, it's very fast. It's within a few seconds.
Right. So, yeah. But you got to add some time for the heat of the die to heat the sensor up enough to trigger the cooler to adjust the chuck temperature.
Yeah, but the chuck temperature can react the chuck itself can react very fast because it's an active heater inside. And it's a combination from the cooling liquid and from the internal heater to control the temperature, and that's just very, very fast. And it's not in milliseconds and maybe in 1 second, but for power which should be dissipated for a longer time, maybe for 1, 2, 3 minutes, then it's working very good. Yeah.
Okay, another question. What is the temperature uniformity across the wafer during test? I guess that would be if you're doing a full wafer parallel.
If you're doing a full wafer in parallel, it's depending a little from the setup. How cold is the liquid which we are using, and actually we're working around a range from 2 to 4 Kelvin. Yeah.
Okay. And next, for the low parallel, high power applications, is the thermal change speed a bottleneck for test capacity? I'm not sure I understand the question, so I don't know if you do. He's talking about TK rise.
Yeah, the thermal change speed. Yes, it's a bottleneck because you have always some delays because of the thermal mass from the system itself, and if you want to react in milliseconds or seconds, it's I think almost not possible because the transition time and the temperature gradient is so high in the wafer. In some point, the chuck can compensate it because with this thermal mass, it's a hard challenge. Yeah.
Okay. Then another question. So should the device temperature be controlled rather than the chuck temperature? So it's very hard to control the device temperature directly because you need a RTD inside the device, which you can read out in some way. Then you have to react with a chuck to control this temperature. But from our understanding, that the wafer itself, it's very thin actually. It's not a big thermal mass, and then if the thermal contact between the wafer and the chuck is very good, because it's a very good surface, very clean and plain surface, then the heat transfer should be very, very good between the chuck and the wafer itself. And then actually it's no really use or it's not really necessary to have active control from the device. Okay, I believe we're done with all the questions. There was another question regarding solution for wafer chuck with lower dimension, 10 by 10. But that I don't know if
I think regarding the chuck size itself, it's 10 by 10 millimeter. It's
those don't exist anymore.
we did some special chucks in the past with some special applications, but very less. Our main focus is really on the wafer test side with 200 or 300 millimeter chucks. Yeah.
Yep. Yeah. Hey, Fernand.
Right.
So the solution you guys are providing. So it's a plate. It's a plate that sits on top of the chuck. Is that correct? And then the wafer sits on top of it, or how?
Yes, it's a new product what we actually developing. It's add-on plate which sits on the top from the chuck, right, with up to actually 21 sensors to have a better surface control. Yeah.
Yeah, no, that's really good. So now you can have zone control, because on just on a chuck by itself you cannot. You know, it's just one huge mass. There's no way you can move that mass around. Or your heat.
Yes, right. But we're using this the dedicated sensor in the chuck, and then you can control this temperature in this area. And that's important during the test. If you have just a small touchdown area and you touch down directly at this sensor or very near to the sensor, then you can control this area, the temperature from this area. All other sensors and the areas around this point are not important because there is no test running.
Yeah. And then one last question: how fast can you change the wafer chuck temperature?
Yeah, it's depending. Usually the wafer test is running on a fixed temperature. You're running.
So I think the better or more, maybe a more specific question: how fast can you change the temperature on your plate? Because that's what the wafer is resting on, right? That's a direct contact to the wafer.
Yes, right. It's the reaction is very fast. It's within a few seconds. If we see some temperature changes on the sensor, it takes a few seconds. Then you can change it. Yeah.
Okay. I think we've covered the questions, and very interesting presentation. You know, I hadn't seen anything that could be able to control at wafer level. So it's very interesting. I'd like to learn more about it.
Yeah, Dave Armstrong had an interesting question. I hope I could answer it. He wrote me directly at the chat. And I think he asked about the thermal load from the probe card. And because if you test on -40 degrees, we had a very low temperature, and you contact the probe card to the wafer, the probe card itself it's not usually temperated. It's around room temperature. And in that point, the probe card is reacting like a heat sink. And then you need this additional power on the chuck, the cooling power, to work against this heat sink from the probe card. And that's the power what we have to cool additionally on the system.
Yeah, you know, the thing that helps there, I think, Fernand, is the thermal transfer is always hot to cold.
Hot to cold, yeah, right.
So that's going to pull it down there. It's rather the other way up to the probe card.
Yeah.
Very interesting, Fernand. Very interesting.
Yeah, I hope so. It was interesting for all.
So Ira, I think that was our last presentation for the day.
I also want to thank our sponsors once again for making this event possible: Advantest, Amcor, Indium, FormFactor, and Nidec SVTCL. Advantest is a global leader in the ATE industry with over 30,000 installed systems using nanotechnology products to support leading edge process nodes with a large global workforce, over 50 countries, working in environmentally sound processes. Amcor, who's providing OSAT services with a focus on technology, quality, and service, certainly advanced packaging, quality first, and service from design and test through drop ship, using a global footprint from around the world, but with local sales and support. And Indium, the premier assembly materials designer and manufacturer of thermal interface materials, solder paste fluxes and preforms, and certainly metals and compounds to solve challenging thermal problems. So once again, I'd like to thank all the sponsors. When you have an opportunity, please thank them yourselves to encourage them to sponsor more great events like Too Hot to Test. And so thank you very much for joining us. And I wish you a good rest of your day and look forward to having you participate at a future MEPTEC event. Thank you.